In this video, we're going to circle back to solving nonlinear circuits with computers, which we usually do using programs called circuit simulators. Circuit simulators work really well, and they're staples of industrial practice. You should assume that you always have one available when you're working on problems or labs. They're like calculators for this class. Use one whenever you want. Simulators are capable of multiple types of simulations, and it's important to know how to use each of them. DC simulations are the first and in some ways the most important of these. DC simulations are used to find the bias points of circuits. You could imagine multiple ways of doing this, like guessing and checking a lot of solutions or using brute force to try every possible solution and seeing what fits. But circuit simulators mostly find bias points using an algorithm called Newton's method. This technique finds the roots of nonlinear systems by making successively better approximations. You calculate your very first approximation by guessing, and then you make successfully better approximations using the slope of the function at your previous guess, and the update equation that relates your next guess to your previous one is given down here. So we repeat this a few times. We take our first guess, slope down to 0, take our second guess, slope down to 0, our third guess, slope up to 0, and you can see that our guesses are converging on our root, on where this function crosses 0. There are lots of things to say about Newton's method. For instance, deciding about how many iterations to pursue before you stop requires a bit of thought. However, we don't have time for all of them, and I want you to just take away the most important detail, which is that DC simulations can fail. That's called non-convergence. And you should be ready to adjust your models or simulations to get around that failure. The most common source of non-convergence are non-monotonic or discontinuous models. So for instance, if our x1 guess had been just a little bit further over, we might have landed there and shot our x2 guess all the way out to a huge negative value. So that's an example of non-monotonicity causing a problem. And if we had a discontinuous curve, then it's possible that our solver would land on the discontinuity and not have a derivative to work with. You can build Newton's method in most programming languages pretty easily, and one of my favorite implementations involves storing a function to the variable x on a graphing calculator, then hitting enter a bunch of times to rerun the function for a better approximation. However, Spice has done a lot of that implementation work for you, because Spice implements an n-dimensional Newton's method solver for systems of nonlinear equations. This is a useful trick, and it could potentially be useful for multiple disciplines, which is actually something that Spice recognized at the start of its existence. The name Spice is Simulation Program with Integrated Circuits emphasis, suggesting that it was intended to be used in other domains originally, though it has mostly come to roost in circuits. The output of a DC simulation is shown over here. It's either a list of voltages and currents with numbers next to them, or if you swept a variable, you'll get a graph showing the voltage and current versus your swept variable. This list of numbers happens with a dot-op analysis, and this happens with a .dc analysis. AC simulations effectively calculate the small signal transfer function of your circuit, so a linearized transfer function from an input to an output. AC simulations assume your input is sinusoidal and small, and then they calculate the transfer function by taking a n-dimensional derivative of your circuit's behavior at its bias point. Because you need the bias point to do an AC simulation, you need to make sure your DC simulation works before you run an AC simulation. That means that it needs to converge and also that it needs to be at the right spot. So make sure you run a DC simulation and check it before running an AC simulation. The output of an AC simulation will look like a Bode plot of some variable in your circuit. So you'll be evaluating, say, V1 at many different frequencies. And if you sweep a variable, you'll get a family of curves on your AC result. Many programs report default to reporting AC outputs as decibels, so make sure you refamiliarize yourself with how decibels work, or change the configuration of your y-axes if you're desperate. But Bode plots are so stereotypically log scale that it's generally a better idea to leave it in decibels. In order for an AC simulation to work right, you need to remember to put a small signal source in your simulation, or otherwise the simulator won't know what to call the input of your transfer function. You often have the option to specify the amplitude of your small signal source, but it doesn't really matter because the AC model is linearized. Your input source amplitude is just going to be multiplied by the transfer function to give you the value of your output variable, of your V1 or whatever. So you can set your input source to whatever's convenient. That's usually either the actual size of your input or just a volt. By setting it to 1 volt, the nice thing is that this plot will just tell you the gain from your input to your measured variable. Transient simulations capture all the nonlinear behavior of a circuit, which often makes students think they're the best simulations. However, transient simulations are computationally expensive, and they don't grant as much design insight as AC simulations in some situations, so you can throw a lot of good time after bad with transient sims. Transient simulations also depend on the DC operating point of your circuit as an initial condition for the transient, which is calculated by finding the evolution of a series of ordinary differential equations that approximate your system. That means that you should carry out a DC simulation before a transient to make sure your circuit is at the correct operating point. I also recommend carrying out an AC simulation before a transient to glean design insight, but that depends a little on situation. The transient makes a great confirmation step to show that your system works, but it should be the last simulation you carry out in this class. Finally, beware of the time step setting on transient simulations. Making it too short will cause your simulation to run for a really long time, but letting it get too large can hide oscillations or other behaviors in your circuit. And so the time step will automatically adapt in SPICE simulators, but you have some control over it, and you should use that control to keep an eye out for suspicious simulation behaviors. So the time step can hide stuff or let your simulator lie to you in one way or another. And the output of a transient simulation is a variable of interest, so V1 again, versus time. So it looks a little bit like an oscilloscope trace, and you'll get multiple traces if you sweep a variable. So in summary, SPICE is a very powerful simulator that can accurately represent circuits, and you should consider yourself to have access to it. You should use it in order to solve your problems. DC simulations find bias points, AC simulations find linearized transfer functions, and transient simulations are full nonlinear behavior of a circuit versus time. Make sure you carry out your simulations in the right order, which is almost always DC, AC, and then transient. And one thing that you always need to bear in mind is that if you set up your simulation wrong, it will tell you something wrong. So it's possible for simulators to lie to you because of bad assumptions that you've baked into them. Your armor against that is to check simulations multiple ways, and your ultimate goal should always be to get analysis, simulation, and experiment to agree. If you have all three of those things pointing in the same direction, then it means each of those error-prone processes are probably correct, and that's how you develop a strong scientific result.